At this very moment, a machine forged by human hands screams through the void at 430,000 miles per hour, fast enough to circle the Earth, before your next breath fades. And yet, if you strapped yourself to that impossible velocity and flew toward the nearest star, you would die of old age 6,000 years before you arrived. The cosmos stretches before us like an ocean with no far shore, and every ship we have ever built is nothing more than a paper boat drifting near the sand. But buried deep within the equations that seem to imprison us, woven into the very fabric of time and motion, there exists a loophole so profound, so beautiful, that it would allow a single human heartbeat to echo across millions of light years. Tonight, we chase that heartbeat. We trace the arc of one finite life stretched across the infinite dark. We ask the question the universe dares us to ask. How far can we actually go before the light inside us fades? If you are the kind of soul who lies awake wondering what waits between the stars, a like or subscribe is the quiet way you tell us to keep chasing these questions. It truly means more than you know. Prepare for a journey through time, velocity, and the architecture of reality itself, beyond comprehension. We begin. The fastest thing humanity has ever created is, at this very second, falling toward the sun at a speed that breaks the mind's ability to understand it. The Parker Solar Probe, launched in the late summer of 2018, has reached velocities exceeding 430,000 miles per hour during its closest dances with our star. Let that number settle into your bones for a moment. At this speed, you could cross the entire continental United States in under 25 seconds. You could stand in New York, blink twice, and the probe would already be past Los Angeles, soaring over the Pacific, approaching Hawaii before your eyes fully opened again. This is not science fiction. This is a real object, built by real hands, screaming through real space right now as you listen to these words. To truly feel how remarkable this achievement is, consider the long, slow history of human speed. For over 200,000 years, the fastest any human being could travel was roughly 25 miles per hour, the speed of a running horse. That was the limit of our ancestors' velocity for almost the entire story of our species. Then, in a blink of evolutionary time, everything changed. By 1900, automobiles pushed past 60 miles per hour. The Wright brothers flew at 34 miles per hour in 1903. Within 60 years of that first fragile flight, test pilots shattered the sound barrier at 761 miles per hour. And by 1969, Apollo astronauts returning from the moon carved through Earth's atmosphere at nearly 25,000 miles per hour, the fastest any human body has ever traveled. The Parker Solar Probe moves 17,000 times faster than those brave Apollo astronauts. 17,000 times. It achieves this not through some massive engine burning fuel in a straight line, but through a delicate gravitational ballet with Venus. Each time the probe swings past that cloud-covered world, it steals a tiny amount of the planet's orbital energy, using gravity itself as a slingshot. Year after year, flyby after flyby, the probe builds speed that no chemical rocket could ever achieve on its own. It is humanity's single greatest achievement in the art of moving fast through the cosmic void. And yet, and here is where the silence of space begins to feel heavy, this speed means almost nothing against the true distances between stars. Our nearest stellar neighbor is a small, dim red dwarf called Proxima Centauri, sitting just 4.24 light-years from Earth. Just. That word hides a distance so vast, it swallows every human reference point. At the Parker Solar Probe's record-breaking velocity, traveling continuously without slowing down, without stopping, without any interruption at all. You would need approximately 6,600 years to reach Proxima Centauri. 6,600 years. Let that duration breathe. A journey beginning when the ancient Sumerians first scratched symbols into wet clay, the very birth of writing itself, would only now be approaching its destination. Every empire that ever rose and fell, every war ever fought, every song ever sung, every child ever born across the entire recorded history of human civilization would fit inside the travel time to our closest neighboring star. The mathematics grow even more unsettling when you measure this against one human life. A human lifetime spans roughly 80 years. Traveling continuously at 430,000 miles per hour for 80 unbroken years would carry you approximately 3 trillion miles. Written out completely, that number stretches across 12 zeros. It sounds immense. It sounds like a distance worthy of the cosmos, but it is not. 3 trillion miles equals roughly 0.05 light years. Not 5 light years, not half a light year, 5/100ths of a single light year. The nearest star system sits more than 80 times farther away than what your entire existence at maximum velocity could cover. You would spend every waking and sleeping moment of your life traveling at a speed that would vaporize you on contact with anything solid, and you would never come close to leaving our stellar neighborhood. You would die in the dark between here and there, having crossed a distance that the cosmos would consider barely a step. There is a frozen shell of ancient comets surrounding our sun called the Oort cloud. It marks the true edge of our solar system, the outermost boundary where the sun's gravity finally releases its grip and interstellar space truly begins. This shell extends up to 100,000 astronomical units from the sun, with 1 astronomical unit being the distance from Earth to the sun, roughly 93 million miles. At humanity's current maximum speed, reaching even the inner edge of this frozen boundary would require approximately 600 years of continuous travel. An entire human lifetime at our greatest velocity would not even escape our own solar system's sphere of gravitational influence. We would die long before leaving the sun's extended family of orbiting debris and ancient ice. And so, you begin to feel it, that quiet weight pressing against your chest, the realization that the universe operates on scales so vast that our greatest triumphs in speed are barely distinguishable from standing still. We built a machine that moves 17,000 times faster than the Apollo astronauts, and the cosmos did not even notice. The stars remained exactly where they were. The distances did not shrink. The silence between here and Proxima Centauri did not get any quieter. But do not let that weight become despair, because what you are feeling right now, this sense of smallness, of impossibility, of a universe designed to keep us caged, is precisely the emotional ground from which the most beautiful revelation in all of physics will rise. The barrier is real, the distances are real, but the universe, in its strange and ancient wisdom, has hidden something extraordinary within the very equations that seem to imprison us. And we are going to find it together. But first, we must understand exactly what we are up against. We must feel the full weight of the cage before we discover the key. So now you know the speed. You know that humanity's fastest creation moves at 430,000 miles per hour and still cannot reach the nearest star within 6,000 years. But numbers on that scale can feel abstract, like distant thunder that never quite arrives. So let us bring this closer. Let us measure the cage not in miles or light years, but in the only unit that truly matters to you and me, a single human life. Imagine you are born aboard a spacecraft, already traveling at the Parker Solar Probe's peak velocity, You do not need to accelerate. You do not need to burn fuel. From your very first breath, you are hurtling through the void, at a speed that would vaporize steel on contact. You live a full life. You learn to walk in the narrow corridors, so you grow up watching the same unchanging stars through thick observation windows. You fall in love. You grow old. You celebrate your 80th birthday, surrounded by the quiet hum of the engines and the deep silence of space. And then, gently, your heart beats its final rhythm. In those 80 years, you crossed approximately 3 trillion miles. And where did that extraordinary distance carry you? Barely past the front porch of our solar system. You covered roughly 0.05 light years. The nearest star still sits more than 80 times farther away. Your entire existence, every joy, every sorrow, every breath, purchased a distance the universe would measure as almost nothing. But perhaps the solar system itself offers a useful boundary. Into perhaps escaping our sun's domain would feel like a meaningful achievement, even if the stars remain beyond reach. So, let us ask a simpler question. Could a single human lifetime at maximum speed at least carry you beyond the borders of our own cosmic home? The answer depends on which border you choose. Most people think the solar system ends somewhere around Pluto, that small frozen world orbiting roughly 3.7 billion miles from the Sun. At the Parker Solar Probe's velocity, you could reach Pluto in about a year. A single year. That sounds promising. But Pluto does not mark the true edge of our solar system. Not even close. The real boundary is the Oort cloud, that vast spherical shell of ancient comets and frozen debris that surrounds our entire solar system like a ghostly cocoon. The Oort cloud extends up to 100,000 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So the outer edge of the Oort cloud sits roughly 9.3 trillion miles away. At maximum human speed, reaching the inner edge of this frozen shell would take approximately 600 years. Reaching the outer edge would take thousands more. Your 80-year lifetime would carry you through only a fraction of this invisible boundary. You would die still wrapped in the Sun's gravitational embrace, still technically inside our solar system, still a prisoner of the star that gave you life. This is not a failure of engineering. It is not a problem that a bigger engine or a better fuel could solve. It is a statement about the true nature of cosmic distance, a distance so profound that it makes our greatest speeds feel like the crawling of an ant across an endless desert. Now, some might wonder about other spacecraft. Perhaps the Parker Solar Probe is the wrong reference point. After all, it was designed to study the Sun, not to travel outward toward the stars. What about the machines we actually sent into deep space? What about the probes that were built specifically to fly away from home and never come back? This brings us to perhaps the most poignant object humanity has ever created. But its story belongs to what comes next. A tale of 47 years of lonely flight, a golden record carrying the sounds of Earth, and a distance so small against the backdrop of the stars that it would break your heart if you let it. Before we go there, though, consider one more thing about what 80 years at maximum speed actually means in the language of light. Light is the fastest thing in the universe. Nothing with mass can ever match it. A beam of light travels at 186,000 miles per second, not per hour, per second. In the time it takes you to read a single sentence, light has circled the Earth 7 times. It reaches the Moon in just over 1 second. It crosses the distance from Earth to the Sun in about 8 minutes. Your 80-year journey at humanity's peak velocity That 3 trillion-mile odyssey that consumed your entire existence covers a distance that light would cross in roughly 16 hours. Not 16 years, not 16 months, 16 hours. Your whole life reduced to less than a single day of light travel. The nearest star, Proxima Centauri, sits 4.24 light-years away. That means light itself needs over 4 years of continuous travel to reach it, and your lifetime at maximum speed equals less than 1 day of what light can do. There is a strange beauty in this cruelty. The universe is telling us something honest. It is saying that the tools we have built so far, magnificent as they are, so miraculous by the standards of our ancestors, are not the right tools for this particular dream. Chemical rockets, gravity assists, even the cleverest orbital mechanics our brightest minds can devise. These are instruments for exploring our local neighborhood. They are boats built for rivers, not for crossing oceans. The ocean of interstellar space demands something else entirely. It demands a different kind of physics, a different relationship with time and energy, a different understanding of what motion even means when distances stretch across light years and centuries. And the beautiful thing is that this different physics exists. It has existed since 1905, written down by a young man who had never even held a university teaching position. But we are not ready for his gift yet. We have one more lesson in humility to absorb first. Because out there, right now, tumbling through the darkness beyond the reach of our sun's magnetic influence, there drifts a small machine about the size of a school bus. It has been flying away from Earth for nearly half a century. It carries a golden record etched with the sounds of wind and whales and human laughter. And after 47 years of continuous travel, it has covered a distance so heartbreakingly small that it will redefine everything you think you understand about how far away the stars truly are, somewhere beyond the reach of our sun's solar wind. In the cold silence between stars, a small machine drifts alone. Voyager 1. Launched in 1977, it has been flying away from Earth for more than 47 years. It is the farthest human-made object in existence. Nothing we have ever built has traveled farther from home. And its journey tells a story that is both magnificent and devastating in equal measure. After nearly 5 decades of continuous flight through interplanetary and now interstellar space, Voyager 1 has covered approximately 15 billion miles. 15 billion. The number feels enormous. It feels like a distance worthy of celebration, and in many ways it is. This small probe, carrying a golden record etched with greetings in 55 languages, the sound of ocean waves, the music of Beethoven and Chuck Berry, has traveled farther than any object born of human imagination. It crossed the heliopause in 2012, officially entering interstellar space. That boundary marks the place where the sun's solar wind loses its battle against the pressure of the thin gas and dust that fills the void between stars. Headlines announced that Voyager had left the solar system, and technically, in one narrow sense, that was true. The probe escaped the sun's magnetic influence, but it remains firmly trapped within the sun's gravitational domain. It will not pass beyond the outer edge of the Oort cloud for another 30,000 years. Voyager 1 has left the sun's magnetic bubble, but it has not left the sun's family. It is like a child who walked out the front door but still stands in the yard, still on the property, still within calling distance of home. Now let us measure what 15 billion miles actually means against the distance to the nearest star. If you scaled the journey to Proxima Centauri down to a cross-country road trip from New York to Los Angeles, roughly 2,800 miles of highway, Voyager 1 would have traveled approximately 100 feet in 47 years. 100 feet. you would still be standing in your own driveway, barely past the mailbox, after half a century of continuous driving. Your neighbors would watch you age from youth to retirement, while your car remained visible from their kitchen window. That is what 15 billion miles looks like against the true scale of interstellar distance. Less than 1,000% of the way to our closest stellar neighbor. Here is another way to feel this. Light travels at 186,000 miles per second. Voyager 1, after nearly 5 decades of flight, has covered a distance that light crosses in approximately 20 hours. The probe's entire 47-year journey equals less than a single day of light travel. Meanwhile, the journey to Proxima Centauri requires over 4 years of light travel. The nearest star sits more than 150,000 times farther away than Voyager has managed to reach in nearly half a century. Voyager 1 travels at approximately 38,000 miles per hour relative to the Sun. This is fast by any earthly standard. But at this velocity, the probe would need over 70,000 years to reach Proxima Centauri. 70,000 years. Homo sapiens emerged roughly 300,000 years ago. Voyager would need to fly for nearly a quarter of our entire existence as a species just to reach the closest star, and it will not survive that journey. Voyager carries a plutonium power source that generates electricity through the slow decay of radioactive material. This power source loses approximately 4 watts per year as the plutonium gradually depletes. By 2025, the probe will lack sufficient power to operate any scientific instruments. By 2036, it will fall completely silent. No more data. No more signals. No more whispered messages from the edge of the solar system. Voyager will continue its journey as a dead artifact, tumbling through the void without purpose or awareness. It will drift for tens of thousands of years, a silent monument to human ambition, never reaching any destination, never being seen again by any human eye. The golden record will play for no one. The sounds of Earth will echo inside a tomb that the universe will never open. There is something deeply moving about Voyager's fate. We built it. We filled it with our music and our voices. We flung it toward the stars with all the hope and courage we could muster. And the universe responded with silence and distance so vast that our offering vanished into it like a whisper into a hurricane. Voyager did not fail. We did not fail. The distances simply exist on a scale that our current tools cannot bridge. Some scientists have looked at these numbers and drawn a grim conclusion. They have said that the universe imposes a kind of cosmic quarantine on intelligent life, that the spaces between stars are not empty voids waiting to be crossed, but walls designed by physics itself to keep living things trapped on their homeworlds. We might send radio signals that take years or centuries to reach distant civilizations, but we could never visit them. We could never touch an alien hand or walk beneath a foreign sun. The cosmos seemed to forbid such dreams through the simple, merciless mathematics of distance and time. And if the story ended here, that conclusion might stand. If chemical rockets and gravity assists were all physics had to offer, humanity would indeed be prisoners of our local star, forever dreaming of shores we could never reach. But the story does not end here. Because the problem is not simply that our engines are too weak or our fuel too limited. The problem runs deeper. It is woven into the most fundamental equation governing how rockets work. A mathematical relationship so unforgiving that it dooms every chemical propulsion system ever conceived, no matter how cleverly designed, no matter how generously funded. This equation explains why we cannot simply build a bigger rocket or carry more fuel. It reveals that the barrier between us and the stars is not a wall that engineering can climb. It is a law of nature that engineering must accept and then find a way around. And finding that way around is exactly what a quiet young man in a Swiss patent office would do, working alone with nothing but a pencil and a question that nobody else thought to ask. His answer would change everything. But before we can understand his gift, we must first understand the prison. We must feel the full weight of the chains before we learn how to slip through them. Those chains have a name. They are called the Tsiolkovsky rocket equation, and their grip is absolute. Every rocket humanity has ever launched works on the same basic principle that carried the first Chinese fireworks into the sky over 1,000 years ago. You throw hot gas out one end, and the reaction force pushes you in the opposite direction. Newton's third law in elegant action, simple, beautiful, and devastatingly limited for the purposes of reaching the stars. The problem is not ambition or funding or willpower. The problem is a mathematical truth written down in 1903 by a Russian scientist named Konstantin Tsiolkovsky. His rocket equation governs the maximum velocity any rocket can achieve, and it depends on just two things. First, the exhaust velocity, how fast the rocket can throw material out its back end. Second, the mass ratio, the difference between the rocket's total weight with all its fuel and its empty weight after burning that fuel. These two numbers determine everything. And for chemical rockets, both numbers are cruel. Chemical propellants max out at an exhaust velocity of roughly 4.5 kilometers per second. This is not an engineering limitation waiting for a clever fix. It is a fundamental ceiling imposed by the chemistry of combustion itself. When you burn hydrogen and oxygen, the most energetic chemical reaction we can practically use, the resulting steam molecules can only move so fast. The energy released by breaking and forming chemical bonds has an absolute maximum. No amount of genius can make those molecules exit a rocket nozzle faster than chemistry allows. The tyranny reveals itself when you calculate what reaching even modest interstellar speeds would require. To accelerate a small probe weighing just 1,000 kilograms to 1% of light speed using chemical rockets, you would need a starting fuel mass exceeding the total mass of the observable universe. Not the mass of Earth, not the mass of our Sun, not every star in the Milky Way combined. The mass of every galaxy, every star, every planet, every atom in the entire observable cosmos would not provide enough chemical fuel to push a small car to 1% of light speed. This is not exaggeration. This is what the mathematics actually demand. The rocket equation contains an exponential function that punishes every attempt at higher velocity with exponentially more fuel. The curve rises so steeply that it quickly exceeds any physically meaningful quantity of matter. So, we look for alternatives. Gravity assists offer some relief. By carefully timing flybys of massive planets, a spacecraft can steal energy without burning fuel. Jupiter has served as our greatest gravitational slingshot, giving thousands of miles per hour to every probe that swung past its massive bulk. But even gravity assists have hard limits. The solar system contains only so many massive bodies, and each gravitational boost adds velocity at the cost of years of travel time to reach the next encounter. A spacecraft optimizing every possible planetary flyby might eventually reach 150,000 miles per hour. Still, tens of thousands of years to the nearest star. An ion propulsion represents the next step. These engines ionize xenon gas and accelerate the charged particles through electric fields. The ions exit at velocities 10 to 20 times higher than chemical exhaust, offering far greater efficiency. The Dawn spacecraft used ion engines to orbit 2 different bodies in the asteroid belt, a feat impossible for chemical rockets of similar mass. But ion drives produce thrust so tiny it defies belief. Dawn's engine generated approximately 90 millinewtons of force. Hold a single sheet of paper flat on your palm. The weight of that paper pressing down equals roughly the thrust of an ion engine. You could run an ion drive for an entire human lifetime and still not reach speeds that meaningfully reduce the journey time to nearby stars. Nuclear thermal rockets climb another rung on the propulsion ladder. These engines pass hydrogen through a nuclear reactor, heating it to extreme temperatures before expelling it through a nozzle. The exhaust velocity roughly doubles compared to chemical combustion. NASA tested this technology extensively during the NERVA program throughout the 1960s and early 70s, running nuclear engines successfully for extended periods. The technology worked. It was ready for deployment. Then, political and budget decisions killed the program in 1973. We have known how to build nuclear rockets for over 50 years, but chose not to. Even so, a nuclear thermal rocket could reach perhaps 100,000 miles per hour. The journey to Proxima Centauri at this speed would still require 28,000 years. Progress, but still longer than recorded civilization. Solar sails offer elegance. They exploit the radiation pressure of sunlight itself, accelerating without carrying any fuel at all. When photons strike a reflective surface, they transfer tiny amounts of momentum. The Japanese Ikaros spacecraft demonstrated this in 2010, unfurling a 14-meter membrane and achieving measurable acceleration from sunlight alone. Close to the sun, a solar sail could accelerate impressively. But as the sail moves away, radiation intensity drops with the square of distance. Double your distance from the sun, and you receive only 1/4 the pressure. A solar sail launched from a close solar approach might reach several 100,000 miles per hour before radiation becomes too weak to matter. At 500,000 miles per hour, faster than any spacecraft has ever traveled, the journey to the nearest star would still take over 5,000 years. A human lifetime at this velocity would cover about 6/10 of a light year. 1/7 of the way to Proxima Centauri. You would still die in the void between stars. This is the devastating landscape of current propulsion. Chemical rockets are fundamentally incapable. Ion engines are too weak. Nuclear thermal rockets help, but not nearly enough. Solar sails cannot push large masses fast enough. Every tool in our engineering toolkit, when held up against interstellar distance, shatters like glass against stone. And yet, the universe is not finished speaking, because the very physics that builds this prison also contains a hidden door. Not a bigger engine, not a better fuel, something far stranger and far more beautiful. A discovery that reveals the cage itself is not what it appears to be. The bars that seem solid are actually flexible. The distances that seem fixed actually compress, and time, that most unchangeable of all things, turns out to be the most changeable of all. The man who found this door was not a professor or a laboratory scientist. He was a 26-year-old patent clerk in Bern, Switzerland, examining other people's inventions by day and reimagining the universe by night. His name was Albert Einstein, and the question he asked was so simple that no one else had thought to ask it. What would happen if you could ride alongside a beam of light? The answer would unlock everything. In 1905, a young man with no academic position, no laboratory, no research funding, submitted a paper to the German physics journal Annalen der Physik. The title was dry and technical, on the electrodynamics of moving bodies. It contained no complex mathematics beyond algebra. It referenced almost no previous scientific literature. It was written by a patent clerk who spent his days evaluating other people's inventions in a quiet office in Bern, Switzerland. And yet this single document would demolish 3 centuries of assumptions about how the universe operates. It would reveal that time itself, that most fundamental and seemingly unchangeable quantity, bends to the will of velocity. Albert Einstein began with a premise so simple it seemed almost trivial. The speed of light in a vacuum remains constant for all observers, regardless of how fast those observers are moving. Whether you stand still on Earth or race through space at half the speed of light, you will always measure light traveling at exactly 186,282 miles per second. This constancy is not an engineering limitation. It is not a measurement error. It is woven into the fundamental structure of reality itself. The universe insists that light speed remains the same for everyone, everywhere, always. From this single premise, Einstein pulled a thread that unraveled everything humanity thought it knew about motion, distance, and time. If the speed of light must remain constant for all observers, then something else must give, as something must flex to accommodate this stubbornness of light. That something turned out to be time itself. Clocks aboard moving vessels tick slower than identical clocks remaining stationary. This effect, called time dilation, seemed absurd when first proposed. How could time, the one thing every human being experiences as perfectly steady and universal, flow at different rates depending on how fast you moved? Surely, a second is a second is a second, whether you are sitting in a chair or flying through space. But the mathematics proved inescapable, and within decades, experiments confirmed what Einstein had derived from pure logic sitting alone in his patent office. Time dilation is not a theory waiting for proof. It is a measured, verified, documented phenomenon. It is as real as gravity, as real as the ground beneath your feet. The relationship between velocity and time dilation follows a precise formula. Einstein introduced a quantity physicists call gamma, the Lorentz factor. This number tells you exactly how much time slows down at any given speed. Without diving into the mathematics, what matters is what gamma does at different velocities, and what it does changes everything about the limits of human exploration. At everyday speeds, gamma barely differs from 1. A car on a highway experiences time dilation so tiny that the most precise atomic clocks can barely detect it. An airplane passenger ages perhaps a few nanoseconds less than someone who stayed on the ground during a cross-country flight. The effect exists, but it carries no practical meaning for daily life. You will never notice it. Your watch will never show it. Time dilation at human speeds is a ghost, present but invisible. The magic begins when velocity climbs toward a meaningful fraction of light speed. At 50% of light speed, gamma reaches 1.15. Time aboard the spacecraft passes about 15% slower than time on Earth. 1 year of ship time corresponds to roughly 14 months of Earth time. Noticeable, but not transformative. You would arrive at your destination slightly younger than expected, but the difference would barely matter. At 90% of light speed, something remarkable happens. Gamma jumps to approximately 2.3. For every year that passes aboard the vessel, 2 years and 4 months pass on Earth, as a 50-year journey at this velocity would see the traveler age 50 years while Earth aged 115. The crew would return to find their grandchildren elderly and their great-grandchildren running the world. Time has begun to stretch in ways that reshape human relationships across the stars. Pushed to 99% of light speed, and gamma reaches 7.1. Now the transformation accelerates dramatically. 7 years pass on Earth for every single year experienced aboard the ship. A decade of ship time corresponds to 70 years back home. A journey lasting 50 subjective years would span 355 years of Earth history. You would depart from one civilization and return to find it replaced by something unrecognizable. At 99.9% of light speed, gamma exceeds 22. 22 years of Earth time compress into a single year aboard the spacecraft. 50 years of travel at this velocity would span 1100 years on Earth. The Roman Empire fell less than 1600 years ago. Your journey would cross timespans comparable to the rise and fall of entire civilizations, and the numbers keep climbing. At 99.99%, gamma exceeds 70. At 99.999%, it surpasses 223. At 99.9999%, gamma climbs past 700. Each additional 9 added to the velocity pushes the time dilation factor higher by roughly a factor of 3. The universe is offering an escalating bargain. The faster you go, the more time it gives you, the farther your finite life can reach. This was Einstein's gift to humanity. Not a faster engine, not a better fuel, but the revelation that the prison we thought we occupied was built on an illusion. Distance and time are not the fixed, rigid quantities that everyday experience suggests. They are flexible. They stretch and compress depending on how fast you move through space. A measuring rod carried by a fast-moving traveler does not maintain the same length as an identical rod left behind. A clock aboard a speeding spacecraft does not tick at the same rate as a clock on Earth. The universe plays tricks with space and time that make the seemingly impossible suddenly achievable. And this was proven, not just with mathematics, but with real clocks on real airplanes. In 1971, physicists Joseph Haffel and Richard Keating flew cesium atomic clocks around the world on commercial airliners and compared them to identical clocks that remained stationary. The flying clocks gained approximately 270 nanoseconds, exactly as special relativity predicted. The effect was tiny because airplane speeds are tiny compared to light, but the effect was real, measurable, confirmed. Time dilation is not a dream. It is a door. And now we must learn exactly how wide that door opens. So now you hold the key. Time dilation is real, measured, proven. But knowing a door exists and knowing where it leads are very different things. So, let us walk through that door together. Let us take the Lorentz factor, gamma, and point it at real stars, real destinations, real places that shimmer in our night sky. Let us discover what one human lifetime could actually reach, if velocity climbed high enough to bend time in our favor. Begin with somewhere close. Vega, one of the brightest stars visible from Earth, sits approximately 25 light-years away. At conventional spacecraft velocities, reaching Vega would require hundreds of thousands of years. No human could survive even a tiny fraction of such a journey. But at 99% of light speed, with gamma at 7.1, the calculation transforms completely. From Earth's perspective, the journey takes approximately 25 years and 3 months. Light speed is light speed, and nothing with mass can exceed it. But from the traveler's perspective, time dilation compresses this duration by a factor of 7. The subjective journey time drops to roughly 3.5 years. You could travel to Vega, explore any planets orbiting that brilliant blue-white star, and return to Earth having aged only 7 years. Earth would have aged 50 years during your round trip. Your children would be older than you remember, but you would have walked beneath an alien sun and lived to tell about it. Push the velocity higher. At 99.9% of light speed, so gamma reaches 22. That same 25-year journey to Vega compresses to barely over 1 year of subjective time. You could visit Vega and return before your second birthday aboard the ship. Earth would age 50 years during your absence, but you would age only 2, 2 years to cross 25 light-years of space. The mathematics sound like magic, but they are written in the same equations that govern every GPS satellite orbiting above your head right now. Now stretch your gaze further. The Pleiades star cluster, that famous grouping of hot blue stars visible to the naked eye in winter skies, lies approximately 440 light-years from Earth. At conventional speeds, reaching the Pleiades would require millions of years. But at 99.99% of light speed, with gamma exceeding 70, the subjective journey time drops to approximately 6 years. You could travel to one of the most celebrated star clusters in human mythology, explore multiple stellar systems within that glittering family, and return having aged perhaps 15 years. Earth would have aged nearly 900 years. The civilization you left behind would exist only in history books, but you would have seen the Pleiades from the inside. The numbers become genuinely staggering as we aim deeper into the galaxy. The center of our Milky Way lies approximately 26,000 light-years away. A supermassive black hole called Sagittarius A star lurks there, containing 4 million times the mass of our Sun, surrounded by dense star clusters and violent phenomena found nowhere else in our galaxy. At 99.9999% of light speed, with gamma exceeding 700, the subjective journey time to the galactic center falls to approximately 37 years. A traveler could leave Earth at age 25, journey to the supermassive black hole at the heart of our galaxy, and arrive at age 62. They would have lived a normal human lifespan. Earth would have aged over 52,000 years during their trip, but the traveler themselves would step out of their spacecraft at retirement age, gazing upon a black hole that warps space and time around it like a stone pressed into silk. Consider what this means. The entire Milky Way stretches roughly 100,000 light-years across. At extreme gamma factors, a single person could theoretically traverse our entire galaxy, passing through spiral arms, crossing star-forming regions, drifting past ancient globular clusters, and experience the whole journey as lasting roughly 140 years of personal time. With life extension technologies that future centuries might develop, a single individual could cross the Milky Way. But why stop at our own galaxy? The Andromeda Galaxy presents the ultimate test of relativistic travel within our local cosmic neighborhood. At 2.5 million light-years distance, Andromeda is the nearest major galaxy to the Milky Way, a spiral structure larger than our own, containing approximately 1 trillion stars. At velocities where gamma reaches 50,000, the subjective journey time to Andromeda drops to approximately 50 years. A traveler could cross the void between galaxies, enter an entirely separate island universe containing 1 trillion suns, and experience the journey as lasting a single human lifetime. Earth would age 2.5 million years during this voyage. The civilization that launched the traveler would have risen, flourished, and almost certainly vanished. But the traveler themselves would have aged only 5 decades. At the absolute extreme, where gamma climbs into the millions and billions, the mathematics permits journeys spanning most of the observable universe within a single subjective lifetime. A traveler accelerating at 1 gravity continuously, a comfortable acceleration that feels like normal weight, and flipping at the midpoint to decelerate, could theoretically reach the current observable horizon in approximately 45 years of ship time. They would age 45 years, while the universe aged roughly 28 billion years. They would arrive at destinations that currently exist only as ancient light reaching our telescopes. Finding those destinations evolved beyond recognition across cosmic timescales. There is something here that deserves a moment of quiet wonder. The same physics that creates the light speed barrier The same equations that say you can never quite reach the speed of light also provide the mechanism that makes that barrier almost irrelevant for the travelers themselves. The universe gives with one hand what it takes with the other. It says you cannot go faster than light, but it also says that as you approach that limit, time itself will slow down so dramatically that distances measured in millions of light years could fall within the reach of a single human heartbeat. This is not science fiction. These are the verified equations of special relativity, confirmed by a century of experiments operating in every particle accelerator on Earth right now. Moons created in the upper atmosphere by cosmic ray collisions survive far longer than their natural decay time, because they travel at nearly light speed. Time dilation stretches their brief existence, allowing them to reach the ground before they vanish. The universe demonstrates this principle every second of every day, raining proof down upon us from the sky. But beautiful mathematics and physical reality are separated by a question that now presses against us with unavoidable weight. If the equations permit these journeys, what stops us from making them? The answer lives in the most famous equation ever written. 3 symbols that encode the terrible price the universe demands from anyone who dreams of riding light. E equals mc squared. 5 characters that changed the world. Most people recognize this equation even if they cannot explain what it means. It appears on t-shirts and coffee mugs and classroom posters. But beneath its elegant simplicity lies a truth so demanding that it stands as the single greatest obstacle between humanity and the stars. It is the price tag the universe has attached to every relativistic journey we have imagined so far, and the price is almost beyond comprehension. Einstein's equation tells us that mass and energy are the same thing wearing different clothes. They are interchangeable aspects of one underlying reality. A tiny amount of mass contains an enormous amount of energy because the conversion factor, the speed of light squared, is such a spectacularly large number. This equivalence has consequences that transform everything about relativistic travel. As an object accelerates toward a significant fraction of light speed, something strange begins to happen. The energy you pump into the object does not produce the velocity gains you expect. Instead, the object begins behaving as though it has more mass than it started with. At 50% of light speed, an object behaves as though it carries about 15% more mass than it possesses at rest. The extra energy seems to disappear into this growing heaviness. At 90% of light speed, the effective mass has more than doubled. The same engine thrust that once produced rapid acceleration now yields sluggish response, as though the spacecraft had suddenly grown enormously heavy. At 99%, the effective mass has increased 7-fold. At 99.9%, the factor exceeds 22. This is why the speed of light represents an absolute wall for anything possessing mass. As velocity approaches light speed, effective mass approaches infinity. Pushing infinite mass would require infinite energy. Since infinite energy does not exist anywhere in the universe, the final approach to light speed becomes something mathematicians call asymptotic. You can get closer and closer, adding 9 after 9 to your velocity, but you can never quite arrive. The universe allows you to approach the speed of light with as many decimal places as your energy budget permits. But it will never let you touch it. The practical energy requirements for relativistic travel are staggering, as consider accelerating a small probe weighing just 1,000 kilograms to 90% of light speed. The kinetic energy required exceeds 10 to the 19th joules. That number contains 20 digits when written out fully. It equals the total energy output of our Sun for approximately 2 seconds, or the entire energy consumption of human civilization for roughly 1 million years. all of that energy concentrated into accelerating a single object smaller than a car. For a crewed vessel capable of supporting human life during an interstellar journey, the mass might reach 100,000 kilograms or more. The energy scales proportionally. Accelerating such a vessel to 90% of light speed would require energy equivalent to the sun's total output for several minutes. Every photon and every particle, every whisper of radiation our star produces in those minutes, all of it focused into pushing one ship toward one destination. And the cost doubles when you remember a simple fact about travel. People generally want to stop when they arrive. Decelerating from 90% of light speed requires exactly as much energy as accelerating to it. You must burn just as hard to slow down as you burn to speed up. A round trip doubles the requirement again. A journey to Vega and back at 90% of light speed would demand 4 times the acceleration energy, an amount exceeding the sun's output for a quarter of an hour. These numbers explain why relativistic travel remains theoretical despite the physics being well understood for over a century. No propulsion system ever built or seriously proposed can deliver energy on these scales. Chemical rockets fall short by billions. Nuclear fission improves the picture but remains hopelessly inadequate. Even nuclear fusion, the process that powers the sun itself, struggles to provide the energy density necessary for practical relativistic propulsion. But there is a gentler path through this energy wilderness. Rather than sprinting to light speed in a violent burst, what if you simply walked? What if you accelerated slowly, steadily, patiently, at a rate your body could tolerate indefinitely? Humans can endure continuous acceleration at one Earth gravity without any discomfort at all. It feels exactly like standing on the ground. You could walk, eat, sleep, and live normally throughout the entire journey. One gravity of constant acceleration is not just survivable, it is comfortable. It feels like home. At this gentle, sustained push, a spacecraft would reach impressive velocities surprisingly quickly. After 1 year of continuous acceleration at one gravity, you would be traveling at approximately 77% of light speed. After 2 years, roughly 97%. After 3 years, you would exceed 99%. The velocity gains slow as you approach the light speed wall, with each additional year adding smaller increments. But time dilation compensates beautifully, compressing the subjective journey time even as acceleration efficiency drops. The journey profile works like this, yet you accelerate at one gravity for the first half of your trip, building speed continuously. At the exact midpoint, you flip your spacecraft around and begin decelerating at one gravity, gradually shedding velocity so that you arrive at your destination at rest. No violent burns, no crushing forces. Just a steady, comfortable push that carries you across light years while your body feels nothing more dramatic than normal weight. This acceleration profile changes the emotional texture of interstellar travel. It is not a violent launch followed by decades of weightless coasting. It is a gentle, continuous journey where artificial gravity comes free as a gift of the engine's constant thrust. You would live in something resembling normal conditions for the entire voyage. The ship would feel like a building on Earth, with floors and ceilings that behave exactly as you expect. Only the view outside would remind you that you are crossing the universe. There is an open debate among physicists and engineers about whether continuous one-gravity acceleration across interstellar distances is achievable with any foreseeable technology. Some argue that fusion propulsion could theoretically sustain such acceleration for years. Others point out that the fuel requirements, even for fusion, become prohibitive over long durations. A few speculative proposals suggest that exotic energy sources, perhaps even the quantum vacuum itself, might someday provide the sustained thrust needed. The question remains unsettled, hovering between engineering optimism and physical limitation. What is settled, however, is that the energy cost is real and enormous. The universe does not offer discounts on velocity. Every fraction of light speed must be purchased with staggering quantities of energy. The equations are generous with time dilation, but ruthless with energy demands. The door is open, but the toll booth stands directly in front of it. So, what engines could actually pay that toll? What machines might bridge the impossible gulf between our current crawl and the velocities where time itself becomes our ally? The answer takes us from nuclear explosions to antimatter annihilation, to beams of light pushing sails thinner than a human hair. The gulf between our fastest spacecraft and the velocities needed for meaningful interstellar travel spans an almost unimaginable distance. The Parker Solar Probe crawls at roughly 0.06% of light speed. Meaningful time dilation begins only above 10%. The transformation becomes dramatic above 90%. Bridging this gap requires engines that do not yet exist, but that physics does not forbid. And some of these engines are far closer to reality than you might expect. The most audacious propulsion concept ever seriously studied by mainstream engineers was born in the late 1950s at the General Atomics Laboratory in San Diego. A team of brilliant physicists asked a question that sounded insane. What if you detonated nuclear bombs behind your spacecraft and rode the blast waves to the stars? Project Orion, as it became known, attracted some of the finest scientific minds of the era. Freeman, Dyson, and Theodore Taylor devoted years to transforming this wild idea into detailed engineering plans. These were not dreamers spinning fantasies. They were serious scientists performing rigorous calculations and conducting real experiments. The concept works like this. A spacecraft carries a large supply of specially designed nuclear devices. These are ejected one at a time from the rear and detonated at a carefully calculated distance. The explosion creates a plasma fireball expanding in all directions. A massive pusher plate at the back of the spacecraft absorbs the momentum from the plasma that strikes it, pushing the vessel forward. Shock absorbers smooth out the violent impulses into tolerable acceleration. The team actually tested this with conventional explosives. They built small models with pusher plates and detonated charges beneath them. The models flew, the plates survived. The shock absorbers worked. Nuclear test ban treaties halted the program in 1963, before atomic tests could happen, but the physics had been validated. Calculations showed that a modest Orion using fission bombs could reach 3 to 4% of light speed. Larger designs using fusion bombs could potentially achieve 8 to 10%. The most ambitious versions might reach 15% or higher. At 10% of light speed, the journey to Tau Ceti, a sun-like star approximately 12 light-years away that may host habitable planets, would require roughly 120 years. Still longer than one human life, but within reach of a multi-generational crew. Time dilation at this velocity provides minimal benefit, compressing the journey by only about 0.5%. But the fact remains, we had a workable design for an interstellar engine in 1960, and we chose not to build it. Project Daedalus, conducted by the British Interplanetary Society from 1973 to 78, refined this concept using fusion rather than fission. The design burned pellets of deuterium and helium, 3 through inertial confinement fusion. Powerful beams would compress fuel pellets until fusion ignited, expelling reaction products through a magnetic nozzle. Daedalus was designed to reach Barnard's star, roughly 6 light-years away, in approximately 50 years at 12% of light speed. The spacecraft would mass 54,000 tons at launch, almost entirely fuel. It carried no deceleration system. It would flash through its target system at 12% of light speed, conducting observations during its brief passage, then continue into the void forever. Project Icarus, initiated in 2009, revisited Daedalus with modern physics and engineering. It confirmed that velocities between 10 and 20% of light speed appear achievable with fusion technology that could be developed within the coming century. At 15% of light speed, Sirius, the brightest star in Earth's sky at 8.6 light-years, would require about 57 years from Earth's perspective. A traveler departing at age 25 would arrive at age 82, having spent essentially their entire adult life in transit. Survival, but hardly comfortable exploration. Antimatter occupies a unique place among these concepts. When matter contacts antimatter, both annihilate completely, converting 100% of their combined mass into pure energy. Compare this to fission at 0.1% and fusion at 0.7%. Antimatter is roughly 140 times more energy dense than fusion and 1,000 times more efficient than fission. A single gram of antimatter annihilating with a gram of normal matter releases energy equal to the Hiroshima bomb. It could accelerate a small probe to velocities chemical rockets could never dream of reaching. An antimatter rocket would direct the annihilation products through a magnetic nozzle. When protons meet antiprotons, the collision creates particles called pions that can be steered magnetically. These decay into muons, then electrons and neutrinos. The exhaust velocity approaches a significant fraction of light speed itself. With roughly 100 kilograms of antimatter, a modest probe could reach 30% of light speed, crossing the 10.5 light-years to Epsilon Eridani in about 35 years. A human could depart at 30 and arrive at 63. But antimatter's fatal flaw is production. It does not exist naturally in useful quantities anywhere in the known universe. Every antiproton must be manufactured in particle accelerators at enormous energy cost. Current global production totals perhaps 10 to 20 nanograms per year. To accumulate 100 kilograms would require 5 billion years of production at current rates. The energy consumed in creating antimatter exceeds the energy it stores by a factor of roughly 10 billion. And the longest anyone has successfully stored antimatter is approximately 16 hours, achieved at CERN in 2023. A scaling from 16 hours to decades represents an improvement factor of 10,000. Antimatter propulsion works beautifully in physics and fails catastrophically in engineering. Beamed energy propulsion sidesteps the fundamental rocket problem entirely. Instead of carrying fuel, you leave the power source at home. Breakthrough Starshot, announced in 2016 with $100 million from Yuri Milner and endorsed by the late Stephen Hawking, proposes using a ground-based laser array to push tiny spacecraft to 20% of light speed. The array would focus 100 gigawatts, equivalent to 100 large nuclear power plants, onto a sail measuring 4 meters across, attached to a chip weighing a few grams. This gossamer vessel would accelerate from rest to 20% of light speed in approximately 10 minutes. The journey to Alpha Centauri would then take about 20 years. The fatal limitation for human travel is stopping. A laser-pushed sail has no way to slow down at its destination. It would flash through its target system in minutes, snapping photographs before vanishing forever. For tiny robotic probes, this might work. For human travelers who wish to actually arrive somewhere, it fails completely. Some researchers propose hybrid approaches. A laser array provides initial acceleration, while an onboard fusion drive handles deceleration upon arrival. Others suggest magnetic sails, superconducting loops generating enormous fields that interact with charged particles in interstellar space, so creating drag to gradually slow the vessel. The Bussard ramjet, proposed in 1960 by physicist Robert Bussard, imagined scooping hydrogen from interstellar space to fuel continuous fusion. It was elegant in theory, but doomed in practice. The magnetic scoop creates more drag than the engine can overcome. More speculative concepts push into uncertain physics. The Alcubierre warp drive describes a configuration of spacetime that contracts space ahead while expanding it behind, carrying a vessel faster than light without violating relativity. The mathematics works within general relativity, but requires negative energy density that may not exist in nature. Wormholes could theoretically connect distant points through shortcuts in spacetime, but require exotic matter to remain stable. The realistic frontier lies with advanced fusion, perhaps augmented by beamed energy. These technologies could plausibly reach 15 to 20% of light speed within the coming century. But between 20% and 90%, where time dilation truly transforms, lies a gap that no known technology can bridge. The universe permits relativistic travel. It has simply set the admission price extraordinarily high. And even if we somehow pay that price, the universe has one final boundary waiting. A limit not of engineering or energy, but of cosmic architecture itself. Imagine for a moment that we solved everything. Every engineering challenge conquered, every energy problem resolved. A civilization so advanced that spacecraft routinely reach 99.999% of light speed at the push of a button. Propulsion technology has become essentially perfect. What then becomes the ultimate limit on how far a human could travel in one lifetime? The answer emerges not from engines or fuel supplies, but from the structure of the universe itself. Even with godlike technology, cosmic geometry imposes boundaries that no civilization can overcome. These boundaries are not walls built from matter. They are woven into the fabric of space-time, enforced by the expansion of the cosmos and sealed by the finite age of everything that exists. They define the absolute maximum reach of any traveler, regardless of velocity, lifespan, or technological sophistication. The observable universe provides our first reference point. This sphere, centered on Earth and extending approximately 46.5 billion light-years in every direction, contains every photon that has had time to reach our planet since the beginning of cosmic time. Its total diameter spans roughly 93 billion light-years. Within this volume exist approximately 2 trillion galaxies, each containing hundreds of billions of stars, each potentially hosting planets where life might have emerged and looked up at the sky with wondering eyes. But the observable universe is not the same as the reachable universe. The distinction matters profoundly. Light reaching Earth today from the most distant observable galaxies began its journey over 13 billion years ago, when the universe was young and small. During that immense travel time, cosmic expansion stretched the space between those galaxies and Earth. Objects that emitted their light 13 billion years ago now reside 46 billion light-years away, carried outward by the expansion of space itself. Space is not a fixed stage on which cosmic events play out. It is a living thing that grows. Galaxies are not flying apart through space like shrapnel from an explosion. Space itself is stretching, carrying galaxies along like raisins in rising bread dough. And this expansion is accelerating. In 1998, two independent research teams studying distant supernovae made a discovery that shook physics to its foundations. The universe's expansion rate is increasing over time. Something is pushing the cosmos apart faster and faster with each passing era. This mysterious force, called dark energy, comprises approximately 68% of the universe's total energy content. We can measure its effects with extraordinary precision. We have almost no idea what it actually is. The discovery earned the 2011 Nobel Prize in Physics and fundamentally changed our understanding of cosmic fate. Dark energy creates a boundary more fundamental than the observable horizon. The Hubble sphere marks the distance at which cosmic expansion equals the speed of light. Objects at this boundary, approximately 14 billion light-years from Earth, recede from us at exactly 186,000 miles per second. Their recession velocity precisely matches the cosmic speed limit. Beyond the Hubble sphere, galaxies recede faster than light. This does not violate Einstein's rules because the galaxies are not moving through space at superluminal speeds. Space itself is expanding and carrying them along. The distinction is real but offers no comfort to travelers. Whether carried by expanding space or moving through it, objects beyond the Hubble sphere are retreating faster than anything could ever chase them. But even the Hubble sphere is not the final boundary. A spacecraft can accelerate continuously, potentially outrunning the local expansion rate at its current position and pushing into regions where even light from Earth could never reach. The true limit is something called the cosmological event horizon. This boundary, currently approximately 16 to 17 billion light-years from Earth, marks the maximum distance any signal or traveler departing today could ever reach given infinite time and unlimited velocity. Beyond this line, cosmic expansion has already won. Space stretches faster than any approach speed could overcome. Destinations beyond the event horizon are not merely difficult to reach, they are impossible, forever, by any means consistent with known physics. And this horizon is not standing still. It is shrinking. As dark energy continues accelerating the expansion of space, the event horizon contracts. Regions accessible today will become permanently unreachable in the future. The window for cosmic exploration narrows with each passing moment. The universe is slowly closing its doors. Current models suggest that within approximately 100 billion years, the event horizon will have contracted to encompass only our local group of galaxies. The Andromeda Galaxy, currently approaching us under gravitational attraction, will merge with the Milky Way long before this isolation becomes complete. But every other galaxy in the observable universe will have crossed beyond the event horizon. They will be gone, not destroyed, simply unreachable, carried beyond any possibility of contact by the relentless expansion of space. On even longer timescales, measured in trillions of years, the isolation becomes total. Future astronomers living in whatever merged galaxy descends from the Milky Way and Andromeda will observe a universe containing only their immediate galactic home. No external galaxies will be visible. The cosmic microwave background radiation, that ancient echo of the Big Bang, will have redshifted beyond detection. Every observational clue that other galaxies ever existed will have been erased. These future astronomers might develop physics and cosmology from first principles, study their local stellar environment, and conclude that their galaxy constitutes the entire universe. They would have no way of knowing that 2 trillion galaxies once filled the sky. The evidence will have been carried beyond the horizon by the very expansion that hides it. The universe will have deleted its own history. There is something deeply unsettling about this cosmic erasure. We live in a privileged moment, an era when the universe still reveals its vastness, when distant galaxies still send their light to our telescopes, when the evidence for the Big Bang still echoes through space as background radiation. Future civilizations may never have access to these clues. They may live in a cosmos that appears small, static, and lonely. The grand story of cosmic evolution that we can still read in starlight will have faded beyond recovery. This creates an urgent countdown for exploration that most people never consider. Every galaxy, every star cluster, every cosmic structure we might dream of visiting faces an expiration date. After that date, the destination becomes permanently unreachable. The universe offers a window of opportunity for exploration, and that window is slowly but relentlessly closing. Perhaps the most haunting number in all of cosmology is this: of the roughly 2 trillion galaxies populating the observable universe, perhaps 1/1,000,000th of them, those within our local supercluster, might theoretically be reachable before expansion carries the rest beyond the event horizon. The overwhelming majority of galaxies we can see today are already slipping away. We observe their ancient light, but we can never touch their shores. They exist for us only as images, light that traveled for billions of years to paint pictures on our instruments, of places we can never go. So, the universe sets 2 prices for cosmic exploration. The first is energy, the staggering fuel cost of relativistic velocity. The second is time, the closing window imposed by accelerating expansion. Both prices are real, both are rising, and between them, they define the true boundaries of how far any human lifetime could ever reach. But within those boundaries, the distances remain breathtaking. Now, we stand at the edge of the most extraordinary calculation in all of human imagination. We have felt the weight of interstellar distance. We have understood the prison of chemical propulsion. We have discovered Einstein's loophole in the fabric of time. We have counted the cost in energy and confronted the shrinking boundaries imposed by cosmic expansion. Now let us gather all of this together and ask the question plainly. If a human being could somehow achieve extreme relativistic velocities, how far could one lifetime actually stretch across the cosmos? At 99% of light speed, with gamma at 7.1, a traveler maintaining that velocity for 50 years of subjective time would cross approximately 350 light-years. Earth would age roughly 355 years during this journey, but the traveler's biological clock would record only 5 decades. This distance encompasses perhaps 50,000 star systems. Within 350 light-years lie stellar nurseries where new stars are being born, ancient globular clusters containing stars older than our galactic disk, and diverse stellar types ranging from dim red dwarfs that will burn for trillions of years to blue giants that will explode as supernovae within mere millions. A single human lifetime at this velocity would open a volume of space containing more worlds than any explorer could catalogue in 1,000 lifetimes. Push to 99.9% of light speed, and the numbers transform dramatically. Gamma exceeds 22. 50 years of shipboard time corresponds to over 1,100 years of Earth time. During those 50 subjective years, a traveler would cross approximately 1,100 light-years, encompassing millions of star systems across a volume containing perhaps 10 billion potentially habitable planets. The Orion Nebula, one of the most spectacular star-forming regions visible from Earth, lies approximately 1,300 light-years distant. At this velocity, a traveler could reach this cosmic nursery, witness the birth of new stellar systems, observe protoplanetary disks coalescing into worlds, and experience one of the most visually stunning phenomena in our galaxy, all within a human lifetime. At 99.99% of light speed, gamma exceeds 70. 50 subjective years now span 3,500 light-years. The Carina Nebula, a massive star-forming region 7,500 light-years away, becomes reachable in roughly 107 years of ship time. The Eagle Nebula, with its famous pillars of creation at 7,000 light-years, falls within similar reach. The deep interior of our galaxy opens up like a flower. The galactic center itself, where the supermassive black hole Sagittarius A star sits surrounded by millions of densely packed stars, lies 26,000 light-years from Earth. At 99.99% of light speed, a traveler could reach this cosmic monster in approximately 370 years of ship time. A multi-generational crew departing Earth when Rome was a young republic would be arriving now, finding themselves at the gravitational heart of everything, gazing into a black hole containing 4 million solar masses of collapsed matter at 99.999% of light speed. Gamma exceeds 223. 50 subjective years would cross over 11,000 light-years. At 99.9999%, gamma exceeds 700. 50 years of personal time would carry you 35,000 light-years, past the galactic center and into the far side of the Milky Way. A single person could theoretically traverse our entire galaxy, 100,000 light-years from edge to edge, and experience the crossing as lasting roughly 140 years. With future life extension, one individual could see the whole Milky Way. And then come the numbers that truly break the mind. The Large Magellanic Cloud, a satellite galaxy of our Milky Way, orbits 160,000 light-years away. At gamma equal to 3200, a traveler could reach this separate stellar system in 50 years of ship time. Earth would age 160,000 years. The civilization that launched them would be ancient beyond memory. But the traveler would have aged only 5 decades and would stand among stars belonging to an entirely different galaxy. The Andromeda Galaxy sits 2.5 million light-years distant, a trillion stars arranged in a spiral larger than our own Milky Way. At gamma equal to 50,000, the subjective journey time drops to approximately 50 years. One human lifetime to cross the void between galaxies, to enter an island universe that has never been touched by any hand born under our sun. Earth would age 2.5 million years. The travelers would arrive as orphans of time, citizens of a galaxy that knows nothing of their origin. Push gamma into the hundreds of thousands, and the great galaxy clusters become theoretically accessible. The Virgo cluster, containing over 1,300 galaxies at 54 million light-years, could be reached in 50 subjective years at gamma, equal to roughly 1 million. The traveler would age 5 decades, while Earth aged 54 million years. Dinosaurs roamed our planet more recently than the traveler's departure would seem to earthbound observers. At the absolute extreme, a traveler accelerating at one comfortable gravity continuously, flipping at the midpoint to decelerate, could theoretically reach the current observable horizon, the farthest edge of everything we can detect, in approximately 45 years of ship time. 45 years, less than a typical career. The universe would age roughly 28 billion years during this journey. The traveler would arrive at destinations that currently exist only as ancient smudges of light in our deepest telescope images. Everything familiar would have vanished into unrecoverable antiquity behind them. But even here, at the uttermost limit of what time dilation permits, the cosmological event horizon remains absolute. The 16 to 17 billion light-year boundary cannot be crossed. Destinations beyond that line are retreating faster than approach. No gamma factor, no matter how extreme, can bridge that gap. The traveler could reach the edge of the reachable universe in 45 subjective years. But the unreachable universe stretching beyond would remain forever silent, forever dark, forever beyond any contact. and so the answer to our question takes shape. Within one human lifetime, the physics of time dilation theoretically permits travel across billions of light years of space. From one tiny world orbiting one ordinary star, a single person could journey far enough to witness galactic superclusters, cross cosmic voids spanning hundreds of millions of light years, and touch the elementary large-scale structure of space-time itself. The universe has not built walls around humanity. It has built highways stretching toward every horizon. Highways we have not yet learned to travel, but that physics declares open to anyone who can master the necessary velocity. Yet every one of these extraordinary journeys carries a cost, measured not in fuel or energy, but in something far more precious, something no equation can calculate and no technology can restore. And it is this cost that transforms the question of distance into something deeply, achingly human. Every journey we have traced across the cosmos carries a hidden weight that no engine can lighten and no technology can remove. It is the weight of time flowing differently for those who travel and those who stay behind. Time dilation gives with one hand and takes with the other. It compresses your journey into manageable decades, but it stretches the world you left behind into unrecognizable centuries. Every relativistic voyage is a one-way ticket through time, and the farther you go, the more completely you are exiled from everything and everyone you have ever known. Consider a journey to the Pleiades star cluster at roughly 440 light years. At 99% of light speed, the outward trip would take approximately 445 years of Earth time, but only about 63 years of ship time. The return journey adds identical durations. The traveler returns to Earth having aged roughly 126 years, finding that nearly 900 years have passed at home. 900 years. The language spoken when they departed would be ancient history. The political systems would be unrecognizable. The cultural values, the music, the art, the humor, everything that made their civilization feel like home would have transformed across nearly a millennium of change. The traveler would return as a living artifact from a vanished age, perhaps studied, perhaps celebrated, but certainly alone. Scale the distance upward and the isolation deepens. A round trip to the galactic center at 99.99% of light speed would return a traveler to an Earth approximately 52,000 years in its future. Modern humans have existed for roughly 300,000 years. The Earth awaiting the traveler's return would be separated from their departure by more time than the entire history of agriculture, writing, cities, and civilization combined. Whatever beings inhabited the planet might not even recognize the traveler as one of their own. A round trip to Andromeda, if somehow achievable at extreme relativistic velocities, would return a traveler to an Earth 5 million years in its future. 5 million years ago, the human lineage had not yet fully separated from other great apes. Whatever creatures walked the Earth upon the traveler's return would be as different from current humans as we are from our most distant primate ancestors. The traveler would step off their spacecraft onto a planet that shares only its orbit with the world they remember. This is what makes relativistic travel fundamentally different from every journey humanity has ever undertaken. The voyages that shaped our history, Columbus crossing the Atlantic, Magellan circling the globe, Apollo astronauts walking on the moon, all maintained connections between travelers and their homes. Letters could be exchanged. Travelers could return to families who remembered them. The bonds between people survived the distance. Relativistic journeys sever those bonds absolutely. The twin paradox makes this personal. Imagine two identical twins. Alice boards a relativistic spacecraft and travels to a star 20 light-years distant at 90% of light speed. Bob remains on Earth. From Bob's perspective, Alice's outbound journey takes approximately 22 years. Her return takes another 22. Bob ages 44 years. He grows from a young adult to a man approaching retirement during Alice's absence. From Alice's perspective aboard the spacecraft, time dilation compresses each leg of the journey. At 90% of light speed, gamma equals approximately 2.3. Her 22-year outbound trip feels like only 9.5 years. Her return feels like another 9.5. Alice experiences only 19 years of travel, while Bob experiences 44. And when Alice returns to Earth, she is 19 years older than when she left. Bob is 44 years older. The twins who were born on the same day are now separated by 25 years of biological age. Alice might still be building her career while Bob is planning retirement. They shared a womb, but time has placed a quarter-century between them. Communication during relativistic journeys faces its own strange distortions. Messages sent from a spacecraft traveling at 99% of light speed toward a star 100 light-years away would take decades to reach Earth. Earth's reply would take decades more to return. A traveler could send a birthday greeting to their grandchild and receive a response from that grandchild's great-great-grandchildren. The conversation would stretch across generations, each reply arriving from a world that had aged years since the question was asked. Information flowing in the other direction carries its own peculiar quality. A traveler could receive broadcasts from Earth during their journey. But time dilation would compress years of Earth transmissions into months of ship time. They could watch decades of Earth history unfold in accelerated playback. Seeing children grow to adults and adults grow old, yes, in fast forward. The news from home would arrive like a time-lapse film of everything they were missing, beautiful and heartbreaking in equal measure. The visual experience of relativistic travel would add another layer of strangeness. Light arriving from ahead of the spacecraft would be blue-shifted, and its frequency increased by the vessel's motion toward the source. Stars ahead would shift from their normal colors toward blue, then ultraviolet, then X-ray frequencies. The familiar constellations would become invisible sources of radiation detectable only through instruments. Light from behind would be red-shifted, stretched to infrared, and then radio wavelengths before fading beyond detection entirely. At 99% of light speed, relativistic aberration would compress most of the visible universe into a narrow circle spanning roughly 16 degrees ahead of the spacecraft. The entire cosmos would collapse into a brilliant point of light directly ahead with utter darkness behind. You would fly through a universe that had folded itself into a single blazing eye, staring back at you from the direction of your destination. The interstellar medium would add danger to this strangeness. Space between stars contains roughly 1 hydrogen atom per cubic centimeter. At low speeds, this sparse material poses no threat. At relativistic velocities, each atom strikes the spacecraft with energy comparable to cosmic ray particles. The ship's forward surfaces would endure continuous bombardment, capable of damaging electronics, degrading materials, and penetrating biological tissue. Magnetic shielding could potentially deflect charged particles, but the field strengths required grow with velocity. Physical barriers add mass that must itself be accelerated, compounding the energy problem. And so, a choice emerges. A choice that physics cannot make for us. A choice that remains fundamentally human, even when its consequences span cosmic distances. Do you choose range or return? Exploration or connection? Discovery or belonging? For one-way travelers willing to abandon their past forever, the theoretical maximum encompasses nearly the entire reachable universe. billions of light years compressed into subjective decades. But every light year gained is a thread cut between the traveler and home. Every increment of gamma deepens the temporal exile until return becomes not just impractical, but meaningless. For those who wish to return within a few centuries of Earth time, maintaining some hope that recognizable human civilization still exists, the practical limit falls to perhaps a few hundred light years, still encompassing hundreds of thousands of star systems, still offering more worlds than any explorer could visit in 1,000 lifetimes, but a tiny fraction of our galaxy and an infinitely smaller fraction of the cosmos. Neither choice is wrong, neither is right. The universe offers the same physics to every traveler and asks only that we choose what matters most, and so we arrive at the end of our journey. Not at a wall or a locked gate, but at a quiet clearing where the mathematics settles into meaning and the numbers become something you can hold gently in your hands. We have traveled far tonight, from the screaming velocity of the Parker Solar Probe to the silent drift of Voyager through interstellar darkness, from the tyranny of the rocket equation to the tender mercy of time dilation, from the birth of relativity in a Swiss patent office to the shrinking horizon of an expanding universe. We have asked how far one human life can reach across the cosmos, and the answer, it turns out, is both humbling and magnificent beyond measure. The universe has not built prisons for biological life. It has not designed the distances between stars as punishments or barriers meant to keep curious creatures locked on their home worlds forever. Instead, it has written into its deepest laws a provision so elegant that it reads like poetry. The faster you move through space, the slower you move through time. And through this single principle, verified, measured, confirmed by a century of experiments, a finite human lifetime could theoretically span distances that light itself requires millions of years to cross. A traveler at 99% of light speed could explore 50,000 star systems within their natural lifespan. At 99.9999%, they could traverse the entire Milky Way in roughly 140 subjective years. At extreme gamma factors pushing into the tens of thousands, a single person could cross the void between galaxies, reaching Andromeda's trillion stars in 50 years of personal time, while Earth aged 2.5 million years behind them. At the absolute theoretical limit, continuous one-gravity acceleration could carry a human consciousness to the edge of the observable universe in 45 subjective years. These numbers are not fantasies. They are the verified predictions of special relativity operating within the measured geometry of our expanding cosmos. The equations are as solid as the ground you rest upon right now. The engineering to achieve these velocities does not yet exist, but the physics permits it. The door stands open. Only the vehicle remains to be built. And yet, what strikes deepest is not the scale of what is possible, but the nature of what it costs. Every great relativistic journey is an act of sacrifice. A traveler reaching Andromeda gains an entire galaxy, but loses their entire civilization. A round trip to the Pleiades returns you to an Earth 9 centuries older than the one you left. A visit to the galactic center exiles you 52,000 years into the future. The universe charges for passage not in fuel or energy alone, but in the only currency that truly matters to a human heart: time shared with the people you love. This is perhaps the most profound lesson hidden in Einstein's equations. The cosmos does not punish exploration, but it does demand honesty about what exploration means when distances stretch across light years. It means choosing between the known and the unknown, between the warmth of familiar faces and the cold beauty of foreign stars, between belonging to your world and belonging to the universe. No technology can eliminate this choice, It is woven into the structure of space-time itself. Some future travelers will choose range. They will push toward the event horizon, seeking the farthest shores accessible to human consciousness. They will accept temporal exile as the price of cosmic discovery. They will become seeds carried by the wind to soil so distant that no root could ever trace its way back to the parent tree. And perhaps that is enough. Perhaps knowing that human awareness touched the shores of Andromeda, that eyes born under our sun witnessed 1 trillion foreign stars from within that distant spiral, would justify any personal cost. Others will choose connection. They will explore within a radius that permits return to a recognizable home. A few hundred light years, perhaps 1,000. Enough to encompass hundreds of thousands of star systems, billions of planets, and wonders enough to fill libraries that would take centuries to read. They will go far enough to discover, but close enough to come back. They will balance wonder against belonging and find that even a small corner of the galaxy contains more beauty than any single lifetime could absorb. The universe does not care which choice we make. It offers the same time dilation at every velocity, the same expansion rate in every direction, the same physics to every traveler who dares to leave home. What we do with these cosmic parameters, how we weigh discovery against connection, range against return, the unknown against the beloved, remains entirely our decision. These are not physics questions. They are human questions, and they will remain human questions even when asked from the bridge of a relativistic spacecraft crossing between galaxies. There is one more thing worth holding as we rest here at the end of this long journey through numbers and starlight. We live in a privileged moment. Right now, in this cosmic era, the universe still reveals its vastness. Distant galaxies still send their light to our instruments. The evidence of the Big Bang still whispers through space as background radiation. The 2 trillion galaxies that fill the observable sky are still visible, still knowable, still within the theoretical reach of sufficiently advanced travelers. This will not always be true. Dark energy is slowly pulling those galaxies beyond the event horizon. The window for cosmic exploration is closing. Future civilizations born 100 billion years from now may look out at a sky containing only their local stellar neighborhood, never knowing that the universe once blazed with 2 trillion galaxies stretching in every direction. They may never learn what we already know, that the cosmos is vast beyond comprehension, populated by structures so immense that light requires billions of years to cross them, and governed by laws so generous that a single human lifetime could theoretically span it all. We know. We can still see it. And perhaps that knowledge carries a quiet responsibility. To dream boldly enough to honor what the universe has shown us. To build patiently enough to develop the technologies that could carry those dreams into reality. And to remember always that the stars are not impossibly distant. They are merely waiting for us to find the courage and the cleverness to reach them. So, let the numbers settle now. Let the velocities and gamma factors and light-year distances fade gently into the soft hum of background thought. You have traveled far tonight, farther than Voyager, farther than light, farther than any human body has ever gone. You have crossed the galaxy in your imagination and touched the shores of Andromeda in your mind. And now, the journey is over. The stars will still be there tomorrow. The equations will still hold. The door Einstein opened will still stand waiting. But for now, let your breathing slow. Let the vast distances compress back down to the gentle space between your heartbeats. You are here. You are home. You are resting on a small blue world that orbits one quiet star among 400 billion others in a galaxy that is itself just one grain of sand on an infinite shore. And that is enough. That is more than enough. That is everything. Close your eyes. The universe will keep expanding while you sleep. The stars will keep burning. And somewhere, in the mathematics of space-time, your future journeys are already written, waiting for the day when humanity finally learns to read them. Rest now. You have earned it.